To give you a crude illustration of what I mean by a bifurcation, if you put a brick on top of a beam, if the beam is strong enough, then it can carry that brick. So we've got the weight and we've got the beam. But what if you put a pretty large weight, or you press down? Here's a gigantic weight. Then this beam, it's not going to stay in the straight position. Instead of staying straight, it'll probably buckle to one side or the other. I'll do that as a dashed line. It might buckle that way, might buckle that way. It'll buckle under a load. So I've got a business card here, business card from my dentist. And right, if I don't put much pressure, this thing doesn't buckle. But once I press it down, oh, it buckles one way. I guess if I kind of gave it a little imperfection the other way, it'll buckle that other way. So this state is stable when I don't press very hard. Once I increase how I'm pressing, so increase the load, now one side or the other is actually the stable state. And this upward position is the unstable state. In fact, I can't even keep it there. I'm kind of just pinching my fingers like a vice. Ugh, okay. So this would be the beam buckling. That's a nice physical illustration. So this is a large weight or load. Okay, so that gives you kind of an idea. Here, weight or the load plays the role of what we're going to call the control parameter or bifurcation parameter. Yeah, so let me give you an idea of what a bifurcation means. Bifurcation, a qualitative change in the dynamics of a system as a parameter is varied. And what are the types of things that could happen? You could have a fixed point changes stability, or new fixed points show up. That's the type of thing that could happen. There's other things too, but these are kind of the simplest. New fixed points emerge, because those are the types that we'll talk about. When the change occurs, that's called a bifurcation point. And sometimes there's more than one parameter that describes a system. So we might think of the bifurcation parameter as that's the knob that we're turning. For the case of the buckling of the beam, the knob that we're turning is how large that load is. And once the load exceeds a certain critical size, that would be a bifurcation point. And we went from one stable point to now 2 stable points and 1 unstable point. Later, we'll find out that is called a pitchfork bifurcation. You can get really mathy about what bifurcation means. You could say the phase space before and after a bifurcation are topologically inequivalent. Like you cannot deform one to the other without puncturing holes or something. But we won't speak of that just yet. But we will start with the most fundamental bifurcation of all. This is the SaddleNode bifurcation. When I say it's the most fundamental, it is the basic mechanism by which fixed points are created or destroyed.
Dr. Ross, I have a quick question. When we're talking about the bifurcation point, is that a point in the space of the parameter?
I'm kind of speaking of it loosely. I mean, yes, in the space of the parameter. It's probably the best way to think of it. Yeah.
Got it. Thank you.
So the SaddleNode, it's not fragile. It's very robust to any kind of perturbations. So these things are actually seen. Some of the other bifurcations we'll talk about are pretty fragile, so you don't really see them. They're kind of approximations, but this one you can really see, and it can be frightening. The prototypical, sometimes I'll write it as SN, SaddleNode bifurcation, is given by a vector field of this form, R plus X squared. It's worth noting, what do I mean by a parameter? X is, in this case, the state of the system. We imagine that that state is changing with time. R, in this case, is it's constant, meaning for any given instantiation of the dynamics, R would be constant. It's not changing with time. And so that gets called a parameter. These things that are states, we might call them states, or we might call them variables. And people might get kind of sloppy. I might get sloppy myself. But when I say parameter, I would never refer to X as a parameter, although some of your other professors would. Say the parameter of the system, blah, blah, blah. I try to reserve parameter for something that is constant as the dynamics evolve forward in time. And then variables are things that vary with time. So I'll try to keep to that. But here R is a parameter and it's real. So it could be positive, negative, or it could be 0. Let me just draw an example here. Another way that we sometimes write things is we put the state in the front and then semicolon and then the parameters, which then just reminds us to the right of the semicolon, those are the parameters. But that's not always followed. All right, so if I were to plot R plus X squared, this is a parabola opening upward. So let me put a parabola opening upward and it intersects. So this is X dot versus X. And this is the point R. So this is the case for R less than 0. And if we were to, for this case, figure out where the fixed points are, well, it's pretty obvious. We got this fixed point, we got this fixed point. We can even figure out where they are. We've got fixed points at X equals plus or minus square root of R. Okay. Now, are they positive or negative? That's pretty easy to figure out. We just look at the, over here where X dot is negative, this is going to the, oops, it's going to the left. And over here where X dot is positive, it's going to the right. So we've got that this point, X equals positive square root of R, is unstable, and X equals negative square root of R is stable. Okay. We could look at changing R, right? If we change R, so let's try R equals 0. What do we get for that case? We get this parabola intersects the x-axis right at 0. And over here, we've got the, oops, I usually was doing orange. Vector field's moving to the right. Over here, the vector field's also moving to the right. I think last time I said, well, this is technically an unstable point because if you were to get perturbed to the right, you leave. But this is sometimes, I think, Strogatz would call this like a half stable point because it looks stable coming from one side and unstable from the other. Technically, it is an unstable point. Now, what if R is greater than 0? You could probably guess what's going to happen. So the parabola is still opening up, and right, it does not intersect the x-axis. So what do we have? We have over here for the left side, things are moving to the right very quickly, but then they kind of enter this bottleneck zone where they slow down, but then they get very quick again. So we might say for this middle case, R equals 0, there's one half stable point. And that's kind of a weird situation. Seems like it's not the generic case. Right? And over here we have 0 stable, 0 fixed points. This half stable point situation we would call the bifurcation. So in this example, we say a bifurcation occurred at R equals 0, or occurs at R equals 0. If R was a knob that we could turn, then for R less than 0, oh, we've got 2 fixed points. For R greater than 0, 0. And there's this very special point. So this is the bifurcation. point. So it's r equals 0. Because if you think about it topologically, the vector field has changed. For this case on the right, where r is greater than 0, the vector field's always pointing in one direction. This case on the left, r less than 0, the vector field actually changes sign. And you can't deform one into the other. So the vector field changed. And one way we can even tell the vector field qualitatively changed is the number of fixed points. So we had 2 fixed points and then 0. And we could do the math like we did last time for getting the linear stability of each point and really verify, yes, the negative point is stable and the positive point is unstable for this case, but hopefully the graphs can convince you and you don't need that. I think graphs and pictures are a form of proof. So there, it's just another kind of logic. If we were to, I'm saying this thing about the vector field is qualitatively changed. Maybe I'll show that in a different form where I'm kind of showing along this vertical axis, I'll put r, and here's r equals 0. So over here we've got r greater than 0, and then we've got r less than 0. And if we were to qualitatively show the vector field, it's arrows moving all the way to the right. And then there's something weird that happens at this point where we've got the half stable point. And then at least for negative values of x is moving to the right. For large values of x, large positive values, x is also moving to the right. And then there's just some weird intermediate situation where it's moving to the left. So this would be, we've got this point, and they move further and further away. So we've got, if we were to actually plot something, it would look kind of like that. These actually form a parabolic curve of where the points are. And usually in what we would call a bifurcation diagram, we wouldn't really plot it this way. It's most common to plot the parameter along the horizontal axis. That's not always the case, but that's the common thing for what we would call a bifurcation diagram. The bifurcation diagram summarizes where fixed points are, where the bifurcation occurs, and even the stability type. So the typical way that this would be depicted for the SaddleNode bifurcation, we've got a parameter along the horizontal axis, and along the vertical axis where you put this x, or the state of the system. And we would use a solid line to depict the branch of stable equilibrium points, and a dashed line for the unstable. So this is the unstable, and then this is the stable. I think that's right. Yeah, if we look up here, yeah, okay. And then over here, I mean, you could also think of just drawing, kind of schematically drawing the what's the vector field doing. And here the vector field just kind of keeps on going. Here the vector field just keeps on going. Okay. So this is called a bifurcation diagram. And what it's showing us is as we tune this parameter, for some values of parameter, there's no equilibrium points. Like there's no way I'm going to actually hit the bifurcation point, even though we refer to it, right? This R equals 0 is the bifurcation. I'm not going to hit that if I'm tuning something. I'm most likely going to be in the R equals positive range or the R equals negative range, which means I have no equilibrium points, or I have two, and it's one's stable, one's unstable. So this is called a, for reasons that are obscure right now, it's called SaddleNode. The unstable branch is the thing called the saddle, and down here is the thing that's called the node. And because they come in pairs, it's sort of like we've got 2 points that kind of, if we were decreasing R from a positive value, it looks like we have 2 points of opposite type emerging out of nothing. So it's a bit like the way that in particle physics, right, you have positrons and electrons kind of emerging out of the quantum vacuum together. It's a very loose analogy. That's not what's happening here. But if you were starting somewhere over here with R positive and then kind of going this way, it looks like, you know, 2 fixed points emerge out of the blue, or out of the blue sky. In fact, this is sometimes called, in addition to being a SaddleNode bifurcation, which I guess I've already said it is, it's sometimes called a blue sky bifurcation. And other names like a fold bifurcation, because it looks like the family of equilibrium points or fixed points is folded, or turning point, because again, they turn. So it's asked, why is R greater than 0? There's some, not half stable. Hopefully that was answered. There's another one. Is it a SaddleNode bifurcation if the 2 fixed points disappear? Yes. So it doesn't matter which way you go, as long as this exists in the parameter. Like, I could define R to be equal to negative rho or something, and then so then it would kind of flip sides. So yeah, it's called a SaddleNode either way you go. And that's the main name that people would use now. There's blue sky. There's also fold bifurcation. There's a question?
Yeah, I have a question. So if this is like some kind of physical system, the state would have to follow the stable line, or is that not necessarily true?
It's not necessarily true. If you're saying it's a, like, what if I'm going to draw a like magenta point up here? If this is where I started, then I'm going to positive infinity. Does that make sense? Okay. Only things that are, this kind of gets the idea of what is the basin of attraction for this stable point, and it's not the entire real line.
Okay, so like I'm talking like if you have like a positive R parameter and like you're able to adjust it, like you said, it's like say a knob you can adjust by experiment, and you like continually adjust it until it becomes negative. Then it just depends on initial conditions whether it would go unstable or stable.
Yeah.
Okay.
And that's what makes it kind of scary, or which stable thing it goes to. So where does this show up? I can give some physical examples, or not just physical examples, but show up. I've seen it in things related to like nonlinear oscillations, and often there'll be some parameter. I won't necessarily say what it is, but you'll have like this stable state you're following, and then the stable state disappears. And what's happened is it's disappeared in a SaddleNode bifurcation, and there was probably some other SaddleNode bifurcation over here. So if I started with my parameter there, And then I tune my parameter greater and greater and greater. Like, oh, I've got this nice stable thing. It's not changing much. And then at some point, oh my goodness, for a small change, I get this huge change where I go to the other stable state. So we might call this stable state 1. And then this is stable state 2. And this thing in the middle is, it's an unstable state. And so this is where it's typically seen. And if I keep increasing my parameter, well, now I'm on this branch. And if I were to now decrease, let me draw that maybe in another color, blue. If I start here, I'm on stable state 2, I go back. Now I go past this bifurcation point, and I'm still on stable state 2 until I get to this point, and then I jump up to stable state 1. And this is where like pairs of saddle nodes or pairs of saddle node bifurcations lead to hysteresis. So this hysteresis means you could actually get a cycle if I adjust my parameter. And I'm usually thinking, I said parameter doesn't change with time, but I'm technically it means the state dynamics are much faster than any parameter dynamics. The parameter dynamics would be like me turning a knob. So you could get what looks like a cycle. In this case, the cycle, I'll draw it in yellow, would be something like this can happen. So even though we said there's the impossibility of cycles, you could get cycle-like behavior if you have parameters that are also slowly changing in time. Okay. There's another example. I wonder if it'll work here. There's this model that I looked at where we were studying gliders. So this is sort of a aerodynamics example, but we were looking at animal gliders and saying, okay, an animal glider is kind of like a flat plate, like this business card. And it's an airfoil, so it has certain lift and drag characteristics or lift and drag curves. So you could look at what's the lift force and the drag force, or the lift coefficient and drag coefficient as a function of angle of attack for various different things. Like this is like a flying lizard, flying squirrel, flying snake. And they have lift and drag curves that will depend on, you can kind of shift where the lift and drag curve is by changing the pitch angle of your object. And the equilibrium points occur where those lift and drag curves intersect this green curve. So wherever you have intersections with this curve, you can have bifurcations happening. So you can kind of see that where this cotangent curve and this blue curve, if I were to kind of move that thing over a little bit, instead of being in 2 points, it'll just intersect in 1. And that's actually a saddle node bifurcation. So we took data for many different things, including flying squirrels. And we're plotting here it's something like a bifurcation diagram where there are stable points and unstable points. And it forms this thing, this generic looking picture of kind of winding saddle node bifurcations. And there could be hysteresis. So if a flying squirrel pitches down and then tries to pitch back up, it might not be able to reach the stable state that it was at. There was a model where some ecologists looked at, these are like patches of plants in the desert. That's what this picture is showing here. So the middle picture, I guess, no, the picture on the right shows it's mostly desert, but with little patches of bushes. And then some of those bushes connect to make the middle picture. And then all of the patches connect to make the picture on the far left. And that's like how much vegetation biomass is there on that vertical axis versus the dryness of the climate. And you might not know, but as the climate gets drier, maybe you pass this point of no return. They call it a critical transition. And then you go from that stable state to another stable state, which is totally barren desert. It's thought this is something that happened to the Sahara. And that's why it wasn't like a drastic thing over time. It kind of happened suddenly a few thousand years ago, that it went from, oh, there's plants here and there to there's nothing. And so that's why I say it's, scary, because for things like climate, where we don't really know the model, we don't know how close we are to that bifurcation point. But you don't have to fret. There's people working on methods to detect how close we are to a bifurcation point. So like if I'm here, can I know that that I'm close to a bifurcation? Yeah, there are ways. There are ways. It's basically how quickly does the system respond to disturbances. By a disturbance, that means my system gets kicked, and then now I'm here. Now I'll kind of oscillate back and forth. You could look at how quick those things oscillate and how it's changing with time to see, oh, are we close to a bifurcation? Because if you're close to a bifurcation, it's a very long time scale and very large oscillations to get back, which you don't want. Because if I'm like right here, if I get kicked large enough, then I go on the other side of that unstable point, and now I'm in the basin of attraction of this other state. There might be an undesired stable state. Here's a kind of analytical example. If I have a system that looks like this, x dot equals r minus x minus e to the negative x, suppose I have secret knowledge that this shows a saddle node bifurcation. I want you to just show that this undergoes a saddle node bifurcation. And you might wonder, well, how do I do that? I can't stare at that and analytically figure out what the fixed points are, but you could do it graphically. How would you do it? You could take this part, r minus x, because that's easy to plot. Let's look at one case over here. R minus x, this is, I intersect the point R, and then this is going down with the slope -1. E to the negative x is going to be exponentially decreasing thing. So here's e to the negative x, and then in blue, I've plotted r minus x. So where that will equal 0 when the line intersects the curve. This is the curve. E to the negative x is a curve, and r minus x is a line. And of course, as you adjust what r is, you're going to get different types of intersections, right? So here I've just sort of chosen a case where, oh, it looks like there's two. Looks like there's two intersection points, right? With one curve intersects the other, that's one curve minus the other equals 0. But for a different value of r, I've got my curve, e to the negative x is the same thing. I probably didn't draw it exactly the same. But as I decrease r, I'm gonna, exactly just intersect that at one point, and then decrease r further, then that'll intersect only at no points. So you could graphically show this, even if you don't analytically show it. So here's R, no intersections, one intersection, two intersections. So hopefully you get the idea. So at this point where, I don't know, what's the value of that? I guess it'd be R equals 1 or something. I don't know. It doesn't quite matter, but there is a bifurcation point. So this is R equals RC. Let's call that R, the critical point. This is R less than RC and R greater than RC. Very close to that critical point. If we were to plot R minus RC, what would we see in terms of points? We'd have, notice I did R minus RC to make my life simpler. There's going to be a pair of points showing up for R greater than RC. And then I guess I could figure out exactly which one's the positive one, which one's the negative one. I could do that later. But let's just say, all right, this I've shown it, where a curve intersects a line. And that's why this is so generic, because I guess in general, there will be curves and there will be lines, and intersections can happen. So we can graphically demonstrate it. I guess you'd have to know something about how to plot e to the negative x. And we could actually go further. It's the point, I think, that's on the right side that's stable. So that means you could figure that out by just plotting what's greater than what direction the vector field's going. So this one intersection where the line and curve, that's a C-U-R, curve intersect tangentially, that's the bifurcation point. This sort of gets to the idea of why did I write r plus x squared? Because most things are not going to look exactly like that, but in some sense, they could always be rescaled to look like that. This is the idea of normal forms, and there's entire classes taught on normal forms. But I just want to give you the idea that in a certain sense, all SaddleNode bifurcations look like x dot equals r plus x squared in a small neighborhood of the bifurcation. So this becomes powerful. That means this is a prototype. It's the prototypical SaddleNode bifurcation. Very close. You might need to do some rescaling of the parameter or the state, but you can make it look like this for any SaddleNode bifurcation that happens. And this is the idea of what's called a normal form. So in the technical literature of dynamical systems theory, prototypical examples of bifurcations, because there's more than just the SaddleNode, but we'll have to talk about that next time, are known as normal forms. And there's probably some reason for that. It's just kind of like the basic form, the canonical form, the easiest to plot and remember form, but they all look like that. And so there's more. If you want to know more about that, you look at this is in section 3.1. Strogatz mentions some of this. The idea is that very generically, when you've got, let me plot x and x dot, there'll be, if you've got a curve f of x, and we're only looking at this region over here, for r greater than the critical point, right? There's no zeros. And if you go r less than that critical point, well, now you've got 2 zeros. Looks like the same kind of curve, which means there had to be some tangential point. In this box, f of x looks like a parabola, and you could locally describe it as r plus x squared, where r is r minus rc. So there could be some rescaling or moving, but x looks like a r minus rc plus b x minus x star for whatever that critical point is, squared, if we were to expand it, where rc and x star are we might call them the bifurcation point, which sort of gets to the question, is the bifurcation point the point in the parameter space or the point in the state? Depending on what your goal is, it could be both. So this is the critical parameter value and state at that value. I guess we'd say fixed point rather than state. And if you stare at this, you'll be like, oh, well, under the proper rescaling, this just is x dot equals r plus x squared. So that's the idea of a normal form. And next time, I'll talk about a couple of other normal forms, something called the transcritical bifurcation, and then the pitchfork bifurcation.